Dave, our first speaker this afternoon is Tanguy, who will tell us about dominant traits and the zeros of two-variate, two-terminal reliability polynomials.
Good afternoon to all, and thank you very much for this very pleasant workshop. So here my talk, so I'll make a brief outline. So it will be devoted to the study of two-terminal reliability polynomials. And in fact, many speakers of this workshop mentioned reliability polynomials, but they were mostly restricted to all terminal reliability polynomials, in which all sides of the graph must be connected. I mean, the probability of this connectivity must be ensured. And I'll talk in a very short introduction of the two-terminal reliability polynomial. And of course, I'll take some examples for very simple cases, and more, I would try to increase the complexity of the graph. But now maybe a few reminders for those who don't know what it is. It's probability that two sides of a given network are connected, provided that each edge or side has a given probability of working properly. So that means you can factor out all the sides' probabilities of working. It's more complicated. So I've got two very simple examples, and we go back to various either series of parallel graphs. Here, if you want to go here from there, and pieces of equipment you are using or whatever probabilities you are considering is P1, P sub 2, B sub m, the two-terminal series reliability will be the product of such probabilities. In the case of parallel configuration, you add some redundancy to the system. So actually, the true parallel reliability will be 1 minus the product of the 1 minus p sub I going from 1 to m. And of course, if you want to keep to a univariate problem, you can replace all these values by a single variable p here, and you have a single variate reliability polynomial. But of course, you have to do some more thing for non-series parallel graph, because in the real world, this stuff is not working for telecommunication operator, for instance, and this configuration is far too expensive because you can't allow to put 2, 3, or maybe 3, 4, 5 links in parallel because equipment is too expensive. So of course, I will go back to a very simple ladder configuration. Why is that considered in telecommunication network? Because basically, if you want to connect one point to a source to a destination T, basically you have a primary path, a backup path, and that would be a parallel graph. But unfortunately, these source and destination may be very far from each other. So the single reliability from the whole for the whole path here may be rather small, and you can improve this reliability by adding rungs of the ladder, actually. And we can choose to label each node or edge reliability by a different value. And that's where we are going back to multivariate analysis, such as was described by Professor Soka. And in that case, the nice thing about this property is that actually the total reliability from the source to the destination can be put under the following form. You have a product of transfer matrices corresponding to each elementary cell that you have added in the graph. And for this purpose, I've shown you this stuff, and you see that each of the reliability of the 3 edges that you added and the 2 nodes can be put as a linear function of each of the parameters. And that's the most general thing you can have.
What are SI and TI?
SI and TI are the upper and lower nodes here.
So I see the nodes as well as edges.
Yes, that's a really, well, two multivariate problem, because you can choose to index different, give for different edges and nodes very different reliabilities or probabilities. So of course we can go back to from multivariate to two-variate polynomials, in which you can replace all quantities related to edges as p, and then all reliabilities for nodes as rho, another variable. And in that case, if you do that, of course you can see that a lot of things get simplified. You have three eigenvalues. The first one is p rho times 1 minus p rho, and the two other ones are just plus or minus, well, very simple roots of a polynomial of degree 2. And of course, in that case, if you want to calculate this stuff, I'm really lazy about this, but I don't like to compute eigenvalues and eigenvectors if I can. I'm just trying to use a generating function. So it's very easy. You know, because of the finite side of the matrix, that must be some kind of recursion relation between successive values of Rn. So you can use the generating function and characteristic polynomial of the matrix just to compute very efficiently this generating function, which is necessarily a rational fraction, n of z over p of z. So the complex zeros of polynomials, well, I'm sure I can skip this slide very rapidly, because you know everything about this, maybe even better than me, actually. And the only difference with what has been presented in this workshop is that actually we have two parameters, p and rho, and we have, of course, we have chosen two different sides of the network, so it's not a graph invariant. The result will be depending on the different side you consider. Otherwise, you have two parameters, so if you can keep the node reliability fixed, you can plot the zeros in the complex plane for each value of rho and see what happens. And basically, rho will keep it real, going from 1 to 0. So if we consider first the simple ladder case, I mean very small thing, that's the case for the perfect node. So I should have had is that actually we know that the limiting curves will be reached for a reasonably large value of n, a repetition of patterns. And in that case, I'm very, very close to the limiting curve. And no, I won't deal with the way that the zeros accumulate near the limiting curve. So what's happening here is from 1, if rho equal 1, and now 0.9, and if rho decreases, you see what happens. The structure of the 0 is slowly expanding as rho decreases to 0. And the results are, of course, not that, not to be too much excited about, because there are not so many changes in the global structure. There's the first thing I should mention is that you have the double roots that some here are located here, that they can be tracked down by simply analyzing the double roots of the denominator of the generating functions. And actually the endpoints may be computed very easily, I mean asymptotically, and you can see that they go to plus or minus I over 2 rho taken to the half power. And similarly, the endpoints on the real axis can be computed exactly, and this gives again similar dependence. On basically the outer shape of the curve is quasi-circular, and the rate of expansion is given by this power law behavior. So now we want to make things a little more complicated, and we consider the K4 ladder configuration. In this case, the transfer matrix is slightly larger because it was 5 times by 5 matrix with all coefficients also given. I won't reproduce it here, but basically it's the same stuff. You have a generating function which is slightly different. The only difference here is that if you consider P and rho reliabilities for each edge and node, we'll only get 3 eigenvalues for a 5 by 5 matrix. And if you consider perfect nodes, there are only 2 eigenvalues. So
Can I ask you a question before you go
Sure.
on about the previous one?
Yeah,
You
sure.
You had S and T at opposite ends in different columns,
yes.
or you could have it in the same column. Are the results the same?
No, they are slightly different because of, I go back to the, okay. So I could have the destination here, and the difference actually is that the sign corresponding to one eigenvalue is plus 1 instead of minus
But
1.
the limiting curves will be the same.
Yes.
Because the transfer matrix is the
Yeah.
same. So in what sense were you saying that it's not that these things that you're computing are I see, the polynomials themselves depend on S and
Yes.
T. But the limiting curves will not really depend on S and T as long as S is at one end and T is at the other.
Yes. That's it. Okay, so now I would like to add also that if you had only added only one diagonal, the matrix transfer matrix would be 4 by 4, and there would be still 4 p and rho eigenvalues. So it depends on the symmetries actually of this stuff. And now another quick animation, and you see what's happening here for perfect nodes, and you see that at the start you have 4 different equimodular curves, and then at exactly 0.8, 3 of them are joined, and the interesting thing here that you see isolated points which appear, and that's was as has been mentioned by Jesper Jacobsen this morning. This corresponds to values of p where the residue of the generating function corresponding to the eigenvalue of highest modulus disappears. And this is very easy to obtain here. So you'll find, okay. 1. So, and what's happening here is also these singular points are expanding from the origin much faster than the regular equimodular curves. So here are very close, very short summary of the result. We have no closed curve on the left part of the complex plane, but different structural changes. First of all, at 0.8, all these curves seems to be smoother or so, and you have isolated points which occur for different critical values of rho. I won't spend much time about this. And of course, these critical points are obtained by the simultaneous, the fact that the rho and p obey simultaneous polynomial constraints. And the different expansion rate are the rho to the minus 1/4, and here 3 isolated points where their expansion rate is with an exponent 1 minus 1/3. And of course, everything can be computed from the generating function. So now, what I would like to do is from multivariate to bivariate, and then we are showed here very repeated pattern. But what happens if you mix these patterns? I mean, you are not always obliged to take K4, 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 C4, C4, C4. So if you change the repetition pattern, are there persistent features, or do something else occur? So in a first step, you can consider the following network in which you have K4 and simple case or C4, K4, etc. And here the number n will correspond to the number of individual repetition patterns. And in that case, you could say, well, maybe we have 5 or 4 and 3 eigenvalues. In that case, even for imperfect nodes, you have only 2 eigenvalues. And I've written them here, so they give you an idea of what's happening. Of course, this eigenvalue is not as simple as what happens for chromatic polynomial, because they are not very simple polynomials. Here you have to solve the equation given by the recursion relation order what do you call that? The polynomial of the matrix, a characteristic polynomial of the matrix. So in that case, we can also try to plot what happens. And here, even for perfect nodes, in this case, you see different structure here, always two curves, I would insist on that, and then another configuration which Professor Biggs mentioned this morning. It's possible to have a line segment here. And actually here, you have a right angle here, because at some point, you have a possibility of a double, instead of having two complex conjugate roots, you have a single real root, and then these endpoints correspond to double roots of the denominator of the generating function. So if you go, as usual, you decrease rho, what's happening is this. Near 0.8, this has nearly disappeared. Actually, the true value is slightly over 0.8, but this line segment has disappeared. And if I further decrease a rho, then it reappears. So maybe I should go back from 1. So you see first the real segment disappears, and then come back. And then you also see these points here are trying to connect. And eventually they do so. And basically what's happening is you have still a quasi-circular curve, but a persistent real axis segment here. And of course there is this profound mistake because I didn't look careful at my note, but actually there is at the beginning an isolated point. So this sentence is not correct. There are a few isolated points, but it's very difficult to see actually. And of course you have a segment, and it's possible to calculate exactly the critical value of rho for which this isolated point and this real segment disappears. And this one is an equation of a polynomial of degree 3 in rho. And the extremities or the endpoint of the segment are also given here by this expression. But basically, the global behavior of the structure is an expansion as rho to the power minus 1/3. And if I want to further complicate things, I can use this different single motif and just repeat it n times. So here we have something that would have 3 eigenvalues, 4, 3, 4, 4, etc. And you have still, in the end, only 2 eigenvalues because most probably of the presence here of this stuff, of this single pattern. That's if you add another k4 or another k4 minus e, it would be much more complex because it would be at least 3 eigenvalues. But the presence of only one C4 in the repetition pattern implies that you have only 2 eigenvalues. So now I took the liberty of not expressing this, the true value, because it would take maybe 1 or 2 pages, and so be careful. So now what would you expect if you replot the zeros of this structure? That you take this one for n equal 1, and you repeat the motif 2, 3, etc. And I've plotted here for n equal 13. And what you see is basically something that looks like the initial stuff, but in which there's some kind of this part are more blown to pieces somehow. You have some equimolar curves, isolated points too, and what's best is just in the next slide is if you decrease rho, you see that things tend to smooth out. And for 0.8, you have nearly no your wiggles on your complex zero structures. And then if you further decrease rho, there is an explosion of this stuff. So here I'm at 10 to the minus 2, so 0.0.1. And you see there are still isolated points, equimodular curves. And if I go further, decided to make it really nasty. And that's what's happening. And for 10 to the minus 10, what you see is, of course, well, that's not obvious here, but actually you have two families of isolated points here of different symmetries. Are here also the outer part here are isolated points, but here and here you have sets of equimodular curves. So you have different rates of expansion. So in this case, there is no segment on the real line, but different features that is an apparent smoothing out of the structure near rho equal 0.8, and different families of either isolated points or equimodular curves, which correspond to different rate of expansion. And the power law behaviors are with exponent 1 minus 1/3, or here minus 4/13. And here again we can find the same exponent and 3/11. So you have actually very different but rational exponent which appear to control the expansion of a different structure of these zeros. So as a conclusion, I would like to mention that the two-terminal reliability network can be expressed also as a product of transfer matrices, so it's not surprising that it's possible to take a case study of what happens for not only one but two different reliabilities. And of course we can have different structures of zeros for a single family of graphs. Just by changing one parameter, you can see the evolution of these zeros from very simple structure to maybe some different structure. And when the building block has a non-simple structure, the number of eigenvalue may be strongly connected to a very specific substructure of the repetition pattern. And of course, you may have coexistence of isolated points or equimodular curves. And the asymptotic shape is not always circular, because you may have some small little regions in which this happens. And of course, I've tried to make some more work on wider graph, but basically the same thing should happen with, of course, more eigenvalue, with a number of eigenvalues, which is more important. So that might be more difficult to see isolated points. And since I'm a bit early, I can, well, of course, bibliography is obvious. I would like to show you, because just a few minutes left, just what happens if you consider a very simple but very wide graph. Because here you can have, it's instead of having n circuits in parallel, you have also added different edges here, and that creates a super redundancy. And in that case, when nodes are perfect, you see something like this. And slowly, as rho decreases, you look, the structure looks like a tropical fish with some big nose. And, well, with, you know, these fins. And at the end is 10 to the minus 3. So what you see is for n equals 150, this structure of 0. But this is only part of the story, because as I don't remember the speaker, but you have to be aware that the density of zeros is not always the same for different part of the algebraic curves. So actually the true limiting curve for this configuration is this one. So you see, for some parts of the curve, it's very, the density of 0 is nearly uniform, or looks like uniform, and some other parts actually are here. So here you don't have isolated zeros, but only a very poor sampling of what the limiting curve should be.
You do compute the limiting curves and not just the finite n.
Yeah,
zeros.
yes. So go back to the two last transparency. And thank you very much. Yes.
What would you see if you plotted the roots for all n up to 150 instead of just n equals 100?
Didn't try that. Sure.
You might get more of the better side.
Yes. I mean, it would fill the might be interesting to see the density plot of the roots, because basically what you have is at the beginning, for instance, you have, in the first case, you had something like this, and this structure slowly expands, so, and this one goes, so basically you would have something which would fill some part of the complex frame here, and this one, so there might be some, I mean, here it's for the C4 ladder, for the, but in some other cases, I'm not sure, you would exclude, I guess, some inner part of the complex plane. But of course, you wouldn't see, this different structure on the real line. You would disappear because it would disappear because you have so many points at it. So basically, maybe it would give a limiting structure here, or maybe here. I don't know, but where no zero can be found. If I may, I had one word. If anybody may have some idea of, for example, the limiting exponent, because as you see, as you have seen, there's different power law exponent for the expansion rates, and I've got only 3 11s, 4 13s, etc. There might be an upper bound to this exponent. I'm not sure what it can be actually. It might be interesting.
I think Gordon wanted to know whether using smaller n as well as n equals 150, it might help to fill in the parts of the curves that are not.
Yes.
I think the answer is no.
Yeah,
I mean, the point is,
true.
in the parts of the curve that are already fairly dense, doing different n's would make it a little denser. It's a little bit like using rational numbers with different denominators to fill in, right? But in the parts of the curve where the density is below 1 over n, then you're not likely to see any points for any n up to your given n. It's just if you want to see points in that region, you've got to go to very, very large n, which is the real advantage of using Baraha-Kahan-Weiss
Yes.
to compute.
You may have a few dots here corresponding to a very small value of n, and then everything is.
Right. I mean, there are many, many cases where if you didn't know Baraha-Kahan-Weiss, if you merely knew how to compute chromatic polynomials up to size 1,000 and then compute roots of polynomials of size 1,000, you would never see the structures that Baraha-Kahan-Weiss tells you.
Interesting.